Each year, the world produces more than 14 billion pencils, a staggering number, enough to line the entire length of the United States over 500 times, proving the astonishing scale of an object that seems so small and ordinary. But have you ever wondered how a single pencil is manufactured and transformed into a multi-billion-dollar global industry? That journey begins in tropical forests and deep graphite mines, where carefully selected timber and layers of rock are crushed and refined to extract pure black cores. From lush forests to dark underground shafts, raw materials travel thousands of kilometers into modern factories, where automation, precision engineering, and massive production lines merge them into billions of pencils serving the entire world. Today, join Agriculture Insight as we uncover how a simple idea became a tool that has accompanied human knowledge and history for centuries. While China dominates the world with more than 50% of global pencil production, operating like the planet's gigantic manufacturing machine, on the other side of the hemisphere, Brazil has emerged as South America's pencil superfactory, home to the largest Faber-Castell facility in the world, where forests are transformed each day into millions of writing instruments distributed across continents. Yet behind these impressive figures lies a fascinating paradox. Pencils have never actually contained lead. The familiar name originated from a 16th century misunderstanding when graphite was first discovered and mistaken for the metal lead, an error that persisted for hundreds of years. And it is precisely that simple carbon core that creates something remarkable. A single small HB pencil can draw a line up to 56 kilometers long, roughly the distance from downtown Los Angeles to Disneyland Anaheim. To understand why a small pencil stands behind a multi-billion-dollar industry, we must return to where the story truly begins, not in the factory, but in the forest. Each year, billions of pencils are produced, creating an enormous demand for carefully selected timber from across the planet. The forests of California red cedar become the ideal starting point, where straight, soft, and dimensionally stable trunks are cultivated for 20 to 30 years for one single purpose: to become humanity's writing tools. Massive old-growth trees with trunk diameters reaching 100 centimeters are typically felled using high-powered chainsaws. Meanwhile, smaller trees are gripped by modern harvesters that cut them at the base, strip away their branches, and section them into logs within seconds, faster than the blink of an eye. In the heart of the wilderness, steel, hydraulics, and roaring engines merge together, turning the forest into a colossal raw material production line operating without pause. Once felled, the journey of the timber has only just begun. In remote and rugged terrains where no roads exist, logs are airlifted by specialized helicopters, lifting massive trunks off mountainsides like enormous cargo suspended in midair. In most industrial forests, however, giant mechanical arms clamp onto each trunk, bundle them together, load them onto heavy-duty transport trucks, and move them along forest roads built specifically for the logging industry. Convoys of timber roll through dense woodlands, cross the icy landscapes of the northern regions, pass over great rivers, and eventually reach seaports, where they continue their voyage aboard colossal cargo ships sailing across oceans. After standing still in nature for decades, these tree trunks now become passengers in a global logistics network, bound for processing plants where the story of a pencil is truly written. While timber leaves the forest to become the pencil's body, elsewhere on Earth, its soul is awakened from beneath the ground. If wood forms the outer casing, graphite is the spirit that writes every stroke, two separate materials converging to create a complete pencil. This mineral is primarily extracted from open-pit mines in China, Brazil, and Mozambique. nations with abundant reserves and relatively low extraction costs. To reach graphite veins buried deep underground, miners descend into dark tunnels where sunlight barely exists. They ride industrial elevators hundreds of meters below the surface, set fuses and explosives, then retreat nearly 300 meters before the earth trembles violently. When the blast subsides, they return through clouds of dust and shattered rock to collect the glossy black graphite blocks. Heavy ore carts are hauled back to the surface using industrial lifts, where even a brief power outage can transform routine work into a life-threatening challenge deep underground. At the surface, the graphite is crushed and processed to separate pure carbon crystals from impurities such as soil, rock, and metal. The result is high-purity graphite powder, often exceeding 90% carbon content, ready for the next stage, forming the pencil core. As timber arrives at factories and graphite travels across continents, the two materials finally converge to form the perfect structure that protects and carries the writing core. From this point on, the crafting process truly begins. Inside the workshop, massive wooden beams are fed into automated sawing systems, where laser beams and infrared sensors continuously measure straightness, density, and grain patterns in real time. Only sections that meet strict standards are sliced into slats 5 to 6 millimeters thick, the ideal dimension to create 1/2 of a pencil body. A deviation of just 0.1 millimeters can cause the pencil to break or sharpen poorly. Each cut is therefore not merely machining, but a precise transformation, the moment a tree trunk begins its evolution into a writing instrument for humanity. After cutting, the wooden slats pass through multi-blade automatic grooving systems. High-speed rotating cutters carve uniform longitudinal channels with tolerances measured in thousandths of a millimeter. A misalignment no wider than half a human hair could throw the graphite core off balance and cause the pencil to snap the moment it is sharpened. While the pencil body is being shaped, on another production line, the graphite core is undergoing its own transformation to become the true heart of the pencil. To create the writing core, graphite powder is blended with clay in ratios so precise that major brands like Faber-Castell and Mitsubishi Pencil guard their formulas almost like high-end perfume recipes. The more clay added, the harder the core and the lighter the stroke. The more graphite included, the softer and darker the line. This is why familiar markings such as H and B appear on pencil barrels, details many people rarely notice. H, hard, is used for technical drawings requiring fine lines. B, black, is preferred for bold artistic shading, and HB represents the balanced middle ground. Next, the cores are dried to remove moisture, then fired in kilns at temperatures reaching 1000 to 200 degrees. This process stabilizes their structure and increases hardness. Finally, the cores are soaked in oil or wax to reduce friction, allowing for smoother writing and less dust during use. Unlike standard pencils, colored pencil cores contain no graphite at all. Instead, they are made from pigments blended with wax or oil, materials that, in the history of fine art, were once more valuable than gold. Each shade of red, blue, or yellow carries its own precise pigment wax-oil ratio, because every color particle reacts differently to light and friction. This means that a box of 120 colors represents 120 independent material formulas. The mixture is thoroughly blended, extruded into strands approximately 17.5 centimeters long, dried, and then tested for color accuracy and brittleness before being inserted into the wooden casing. Because colored cores are not fired at high temperatures like graphite, they remain softer and more fragile, requiring transportation and assembly processes executed with near handcrafted precision. Once completed, the graphite or colored core is precisely placed into the pre-carved grooves using a high-accuracy automated system. A second wooden slat, coated with specialized adhesive, is then laid on top, firmly enclosing the core in the middle to form the well-known wood sandwich structure, a design that originated in the 18th century and has endured to this day thanks to its exceptional stability. The entire wooden block is then subjected to hydraulic pressing with forces reaching up to 5 tons, ensuring the core remains perfectly centered and durable throughout the pencil's lifespan. From that moment on, wood and core are no longer separate components, but fused together as one, officially becoming a complete pencil. After the wood sandwich block is fully stabilized under pressure, it moves into the shaping stage. The long wooden strips are cut into standard 17.5 centimeters lengths, then fed through high-speed milling systems to form their final shape. Most commonly the hexagonal design, which prevents rolling, saves material, and provides a more balanced grip for extended writing. Next, each pencil undergoes strict quality control. Cameras and precision sensors detect off-center cores, microscopic cracks, or abnormal vibrations before the product is approved for market release. After shaping, the pencil enters the coating stage. Each one is finished with 3 to 6 layers: primer, color, and a final protective coat. The iconic yellow, long associated with pencils, was originally used to promote Chinese graphite, considered the finest in the world during the 19th century. Today, manufacturers also use red, black, blue, or even natural wood finishes. The paint is not merely decorative. It protects against moisture, prevents decay, and allows the barrel to withstand thousands of sharpenings without cracking. Once fully dried, the pencil moves to the branding stage. High-speed printing machines stamp the brand name, product code, and hardness grade, such as HB, 2B, or H, onto the barrel, part of a classification system that can include more than 20 distinct levels. A single small marking determines whether the pencil is suited for everyday writing, technical drafting, or artistic sketching. In the final stage, many pencils are fitted with the savior of every writing mistake: the eraser. The metal ferrule is stamped from thin coils of aluminum or brass, forming small ridges that grip the barrel tightly. Inside sits an eraser made from synthetic rubber, blended with softening agents and ultra-fine abrasives, designed to lift graphite cleanly from the paper. The entire ferrule and eraser unit is then automatically crimped onto the end of the pencil by precision machinery. For pre-sharpened pencils, the last step is revealing the writing core. Industrial sharpening machines with fixed blades create an almost perfect angle, ensuring smooth, consistent lines from the very first stroke. Sensor systems automatically adjust the cutting depth based on the hardness of the core to prevent breakage. Before leaving the factory, every pencil must pass a final inspection: barrel straightness, core alignment, paint consistency, and the firmness of the eraser. Only those that meet strict standards are sorted and packaged into boxes of 6, 12, or 24, in recycled paper sleeves, clear plastic cases, or even premium tin boxes. From distribution centers, they are shipped across the globe. Remarkably, an average pencil can write more than 45,000 words or draw a line up to 50 kilometers long. From classrooms and laboratories to art studios, billions of human ideas begin with nothing more than a single stroke of graphite. The journey of plastic recycling begins the moment empty bottles are discarded, after they have fulfilled their original purpose. From crowded supermarkets, schools, and offices to small residential neighborhoods, millions of plastic bottles are collected every day through recycling bins placed everywhere. However, not all places operate in the same way. In the United States, only 10 states, such as California, Oregon, and Michigan, apply a deposit refund system. Under this system, consumers pay a small deposit when purchasing bottled drinks and receive it back when they return the empty bottles. Thanks to this mechanism, the recovery rate of plastic bottles in these states is twice the national average, turning used bottles into items with cash value the moment consumers finish drinking. After that, teams of workers and specialized trucks travel throughout the city, collecting sacks full of plastic bottles and compressing them into massive containers. Each truck can carry tens of thousands of bottles, equivalent to about 20 tons of plastic in a single trip. When arriving at transfer stations, the entire load of plastic bottles is unloaded in just a few minutes through conveyor systems or tipping mechanisms. Dozens of tons of plastic bottles cascade into the collection yard, forming enormous mountains of plastic that shimmer under the sunlight, blending shades of green, blue, transparent, and many other light hues. These huge masses of raw material are then fed into processing lines, where modern technology begins transforming waste into clean material, ready for a new life cycle. To transform chaotic piles of collected plastic bottles into a consistent material stream, recycling facilities rely on a preliminary sorting stage where human labor and technology work closely together. Although 7 major plastic types exist, each marked by a recycling symbol, only PET and HDPE are commonly recycled into new products at scale. Therefore, the entire system is designed to preserve these 2 plastics while removing unsuitable materials as early as possible. The process begins when mixed plastic waste enters a massive rotating steel drum, perforated with rows of holes. As tons of bottles and packaging tumble inside, dirt, sand, and small debris fall through the openings, while larger plastic items continue moving forward. This step separates materials by size and prepares them for more precise sorting downstream. Next, conveyor belts carry plastics through manual sorting lines. Workers stationed along both sides quickly remove contaminants such as metal cans, plastic bags, and cardboard. At the same time, automated cutting blades detach caps and labels, often made from different plastics. Magnetic sensors extract small metal fragments like staples or leftover can lids. After this combined screening, the material stream becomes uniform, consisting of PET bottle bodies that are cleaner, purer, and ready to enter the next phase of the recycling journey. After sorting, rigid plastic bottles are fed into a shredding chamber where hundreds of alloy steel blades spin at extreme speed, producing a sharp, piercing noise that echoes through the factory. In moments, each bottle is ripped into countless uniform fragments only a few inches long, small enough to slide along the conveyor like a stream of glittering plastic sand under bright lights. The sheer power of these machines is astonishing. Each hour, they can process up to 3,000 pounds of plastic, quickly transforming mountains of bottles into tidy flakes within minutes. Shredding does more than reduce size. Finely chopped plastic melts far faster inside the extrusion furnace, saving up to 40% of energy compared with melting whole bottles. As a result, the entire production line runs faster while significantly lowering operating costs, creating a strong foundation for the next stage of high-tech sorting. This efficiency makes large-scale plastic recycling faster, cleaner, and more economically sustainable worldwide today. From these tiny fragments, optical technology and artificial intelligence handle the most delicate sorting stage of the entire process. A network of high-speed cameras scans each piece, analyzing color and surface structure within milliseconds. When the system detects clear PET, blue PE, white PE, HDPE, or foreign materials such as wood, ceramic, or glass, a burst of compressed air is instantly triggered, blowing that fragment out of the main material stream. The accuracy is astonishing. Each air jet targets a single plastic piece weighing less than 1/1000th of an ounce, without disturbing neighboring fragments. On average, an optical sorting machine can process more than 10,000 pieces per second, with over 95% accuracy, equivalent to the output of hundreds of workers operating continuously without rest. Every second, tens of thousands of particles are separated precisely, forming streams ready for next stage. From the initial state of chaos, the material fragments are now pure enough to enter the pelletizing stage. After sorting, plastic flakes are fed into an extrusion system, where temperatures rise beyond 520 degrees. Under this intense heat, each fragment melts and blends into a thick plastic flow, moving forward like a stream of artificial lava. Inside the machine, a massive screw rotates continuously, mixing the molten material while steadily pushing it ahead. As the plastic travels along the length of the screw, pressure gradually increases, forcing the melt forward. When the material reaches the desired viscosity, it is pushed through ultrafine metal screens that trap the final impurities. At this stage, the molten plastic is cut into countless tiny pellets and immediately cooled with water to solidify their shape. Uniform in size, smooth-surfaced, they sparkle like gems. From uniform PE pellets, the manufacturing journey moves into a defined stage. Preform production, the foundation on which the final shape of the product is created. Inside the factory, material that has passed quality inspection is fed into a heating system, where temperatures rise to around 480 degrees, softening the plastic and preparing it to flow into molds. The result is a short component shaped like a test tube, known as a preform. Each preform has a thick body, while the neck is already formed with threads for a cap. Designed to withstand high temperatures and mechanical pressure, preforms maintain stability throughout transportation and subsequent processing. The advantages of preforms are not limited to technical performance. Their compact size optimizes storage and logistics, allowing millions of units to be transported efficiently without occupying excessive space. For this reason, many facilities specialize solely in preform production, supplying beverage companies, where they are blown into finished bottles closer to points of consumption. When the preforms are ready, they enter a decisive stage, blow molding, where they take on the true form of a plastic bottle. The preforms are fed into a heating system, warmed just enough for the plastic to become flexible while maintaining structural stability. Immediately afterward, high-pressure compressed air is blown in through the neck, causing the plastic walls to expand evenly and press tightly against the metal mold surface, precisely engineered to the desired shape. A 1.5-liter bottle preform, initially only about 10 to 12 centimeters long, can stretch 4 to 5 times its original height during the blowing process. This technique is considered one of the most precise and highly automated stages in PET bottle manufacturing. Each system can produce thousands of bottles within seconds, with deviations controlled to minimal levels. Wall thickness, cap thread accuracy, concentricity, and surface gloss are continuously monitored by sensors and computer software. The result is a lightweight bottle that remains strong enough to hold carbonated beverages, resist leakage, and maintain its shape under pressure. Beyond meeting technical standards, this process offers remarkable flexibility. Bottle volume, body curves, label placement, and even embossed logos can be customized to meet brand requirements. It is here that a simple plastic preform is transformed into a complete PET bottle, ready for cooling and packaging. Immediately after leaving the blow mold, the bottle surface remains at very high temperature, making the plastic walls soft and easily deformed if not treated at once. For this reason, production lines guide bottles into an instant cooling system. Streams of cold air or circulating water stabilize the bottle structure. This rapid cooling process allows the material to harden quickly and retain its original shape. Notably, in modern factories, cooling speed is calibrated with extreme precision. A newly formed PET bottle can reach a safe temperature in under 5 seconds. In addition, many systems recover heat released from bottles to warm water or air, saving energy and reducing operating costs. Once the plastic has fully solidified, the bottle gains mechanical strength needed for stacking, labeling, and withstanding impacts during transportation. Cooling time is calculated to avoid slowing production lines while ensuring clarity and rigidity. When the bottle body is fully stabilized, the journey continues with a rigorous inspection stage to ensure quality before the product reaches consumers. The inspection line is equipped with sensors, cameras, and high-precision measuring devices. Each product is scanned to detect cracks, air bubbles, or dimensional deviations. In addition, random samples undergo mechanical tests such as tension, compression, and impact to evaluate strength. For bottles intended for food and beverages, laboratories conduct chemical analysis to ensure no harmful residues remain. Only after passing this entire strict sequence of checks is the product allowed to move to the next stage. Approved bottles are grouped into large batches, stacked on pallets, and wrapped in protective film. Automated robotic palletizing systems arrange thousands of bottles, containers, or plastic products neatly and accurately. Each batch is labeled with traceability codes, ensuring full transparency from recycled raw materials to finished goods. Products ship from warehouses, completing a circular journey. In the United States, the reality of plastic recycling contains many darker sides than labels often suggest. Only about 5% of plastic bottles are actually recycled, while most of the remainder is buried in massive landfills or sent to incinerators, continuing to place heavy pressure on the environment. For many years, the United States, along with other developed nations, relied on exporting millions of tons of plastic waste to Asia, with common destinations including China, Malaysia, Vietnam, and Thailand. However, in 2018, when China issued a ban on plastic waste imports, that door suddenly closed, forcing the United States to confront the enormous mountains of waste it had created itself. Even so, some plastic continues to be shipped to other developing countries, where waste management capacity remains limited. As a result, large quantities of waste are discharged directly into rivers and oceans, further fueling a new wave of global pollution. This practice worsens ecosystems and threatens wildlife across continents worldwide and future human health. Here, the trees are no longer fully sheltered, but gradually adapt to sunlight, wind, and natural environmental fluctuations. They are organized into plots based on age and growth rate, with water and nutrients continuously adjusted over many months, even years, to prepare them for a stable and sustainable life in plantation forests. After leaving the nursery, young Christmas trees officially enter the stage that will shape their future. Before being planted permanently in the field, each tree is strictly graded based on height, root system health, and growth rate. The soil is carefully plowed into straight, uniform rows, with spacing of approximately 1.8 and 1.8 meters per tree, wide enough for roots to penetrate deeply and for the canopy to develop evenly over time. Planting is carried out continuously, combining machinery with manual labor. Each tree is positioned perfectly upright, its roots placed directly into moist soil, then backfilled and secured immediately. During this early stage, irrigation must be precisely controlled, as even a minor deviation can result in the loss of an entire planting block. As the trees grow, protective netting systems are installed to shield the terminal buds from strong winds and frost, because a single injury to the top shoot is enough to permanently destroy a tree's commercial value. Few people realize that trees in the wild rarely grow into the perfectly conical shape we associate with Christmas. That is why, throughout their growth cycle, Christmas trees undergo repeated annual pruning, carefully shaping each tier of branches while keeping the central leader perfectly straight. In some seed-growing regions, branches are even fitted with pollination bags to control genetic sources for the next generation. But the reality is unforgiving. 30 to 40% of trees are culled before maturity due to crooked growth, uneven canopies, pest infestations, or damage sustained after each pruning season. Only a small fraction prove flawless enough to survive the process and make it to the holiday season. As winter approaches and the trees reach full maturity, the Christmas journey enters its final stage, harvesting and transportation, the most labor-intensive and costly phase of all. On large-scale farms or in deep forest plantations, a mature Christmas tree typically stands between 2 and over 4 meters tall, with a thick trunk and a weight ranging from 30 to 60 kilograms, depending on the species and branch density. Depending on their intended use, trees are handled in 2 ways: cut close to the base for the traditional cut tree market, or lifted with their root balls intact for public squares, shopping centers, and large display spaces. Before leaving the forest, all branches are passed through specialized tree baling machines, compressing each tree into a slender, elongated shape. This process not only protects the needles but also reduces volume by more than 50%, a critical requirement for long-distance transport. In steep, roadless areas, helicopters are deployed to airlift bundled trees out of the forest. A costly solution, but often the only viable option. On farms located closer to populated areas, trees are transferred onto sorting conveyors, where their height and trunk diameter are recorded before being loaded onto specialized transport trucks. From remote forests to brightly lit public squares, each Christmas tree must pass through a complex logistics chain to arrive in time to stand beneath the lights of the holiday season. As snow-covered trees leave the deep forests and arrive at processing facilities, their destinies begin to diverge. The tallest, straightest trees with the most balanced canopies are selected to become holiday icons in major public squares. The Christmas tree at Rockefeller Center, standing at around 75 feet tall and weighing over 10 tons, is not merely a decoration, but a cultural ritual that has endured for decades. Other trees are assembled around steel frameworks, layered into massive structures that blanket entire plazas, where each individual tree contributes to a collective symbol. The rest follow a quieter path, finding their place in warm homes and bustling shopping centers, becoming part of countless private moments of the season. Yet not every Christmas tree is destined to stand whole beneath the glow of holiday lights. Many branches are separated to become decorative materials. Here, wreaths begin to take shape on steel wire frames bent by machines, formed one by one with precisely controlled size and curvature to ensure perfect roundness and structural strength. Onto these frames, each pine branch is carefully trimmed and layered by hand, building thickness and a naturally full appearance. Once the greenery is complete, artisans gently add red bows, dried pine cones, and wintergreen accents, allowing every element to blend together, transforming a simple technical structure into a decoration filled with the warmth of Christmas. After final inspection, the wreaths are carefully packed into specialized boxes and leave the factory, ready to become part of the festive spaces of countless homes. Farewell to natural Christmas trees, grown from soil and sunlight. The Christmas journey now turns toward a different world, where steel, plastic, and industrial assembly lines begin to replace green forests. Growing a natural Christmas tree takes more than 3,000 days and over 1,000 liters of water. An artificial tree, by contrast, is created inside a factory, where the process begins with steel and welding flames. Steel tubes are bent into primary circular frames, then welded to vertical support rods to stabilize the entire structure. Once the frame is complete, a layer of polyester powder is sprayed onto the metal surface, then heat-cured and rapidly cooled to form a durable finish. Finally, the components are assembled and secured with bolts, preparing the frame for the attachment of branches and the completion of the artificial Christmas tree. Once the steel frame is complete, the journey of creating the tree's needles begins. First, green PVC plastic strips are fed into a high-pressure cutting unit, where steel blades operate continuously under pressures of approximately 20 to 40 bar, strong enough to slice the plastic into fine needle-like shapes that closely mimic real pine needles. However, the material is not cut all the way through. The process is precisely calibrated to leave a rigid central spine intact, serving as the structural axis of each needle cluster. This allows the artificial needles to remain tightly connected, hold their shape when spread out, and stay flexible enough to be bent repeatedly without separating or deforming. But for these needle clusters to truly behave like real branches, a thin galvanized steel wire, soft, highly elastic, and small in diameter, is introduced into the production line as a backbone. This wire runs parallel to the green and brown PVC strips, which are then tightly twisted together by a continuous coiling system. The brown strip is positioned at the core to create the visual illusion of a woody branch. Through this constant twisting motion, lengths of artificial greenery are produced non-stop before industrial cutters slice them to precise standard lengths, ready for assembly. Beyond the traditional green, branches can also be flocked with artificial snow or sprayed in a variety of colors, giving artificial Christmas trees a wide range of appearances suited to different festive spaces. Thanks to this closed-loop process, cutting, shredding, and twisting, the production line achieves impressive speeds, generating up to 50 meters of artificial needles per minute, while minimizing waste and optimizing costs. It is this engineered structure that allows artificial needles to maintain their shape across many holiday seasons, something natural foliage can rarely achieve. Once the steel frame is ready, and each artificial branch has been fully formed, the two material streams meet at the final assembly stage. Dense clusters of green foliage are fixed onto the steel skeleton in a precise sequence, starting with the main load-bearing rings and gradually extending across the entire structure. Pneumatic presses secure the branches firmly to the frame, allowing the foliage to wrap seamlessly and evenly around the structure. When the top section is bolted into place, the artificial Christmas tree quickly takes its final form, completed in a single day, in contrast to the many years required for a real tree to grow. Whether grown over many years in deep forests or assembled from plastic and steel inside factories, a Christmas tree becomes the heart of the holiday the moment it enters a living space. Wrapped in lights, ornaments, and ribbons, its branches turn into a gathering point of warmth, reflection, and seasonal glow. From seeds or industrial assembly lines to the moment it stands in a living room or a public square, every Christmas tree carries a long journey hidden behind its shimmering appearance. It is this contrast between years of quiet labor and moments of fleeting joy that transforms the Christmas tree into a symbol far greater than decoration alone. Eating a banana means throwing away the peel. That's obvious. But did you know that in many tropical countries, especially the Philippines and India, nothing from this zero-waste plant is discarded, not even the trunk? What was once cut down and left behind after each harvest is now collected, stripped into fiber, and recycled into high-value natural materials, generating tens of millions of US dollars each year for local communities. In the Philippines, the cradle of the global banana fiber industry, the Abaca banana is cultivated exclusively for fiber across hundreds of thousands of hectares, providing livelihoods for more than 1 million farmers and rural workers. Each year, this fiber brings in over 100 million USD for the Philippines and is recognized worldwide as one of the most durable, water-resistant, and strategically valuable natural fibers in the world. To produce natural banana fiber, the first step begins right in the field. After the banana bunches are harvested, the trunk is immediately cut down while the fiber content is at its optimal quality. A single decisive and precise cut is enough to bring down a banana trunk weighing dozens of kilograms. No machine can replace the hands and experience of farmers at this stage, as even a slight mistake in timing or cutting angle can significantly reduce the quality of the fiber obtained. After being cut down, the entire banana trunk is quickly loaded onto trucks and transported to a pre-processing facility near the field as fast as possible to prevent moisture loss and fiber oxidation. At this stage, the banana trunk is split lengthwise and peeled into individual sheaths. This is a critical step that directly determines the length and uniformity of the fiber, requiring steady hand control and practical experience. Ideally, the outer sheaths, where the cellulose fiber bundles are fully developed, yield the longest, strongest fibers with the least impurities. Farmers use specialized knives to carefully separate each layer along the natural fiber grain, avoiding damage or breakage to the fiber bundles inside. Despite modern tools, this step remains difficult to automate, as variations in trunk thickness and fiber structure still require human judgment. Each banana sheath is fed through a mechanical press or a manual stripping table to remove the soft pulp, leaving behind long bundles of cellulose fibers. Steady hand movements and precisely controlled pressure prevent the fibers from breaking, producing rough fiber strands with a characteristic ivory color. In practice, this work is far from easy, as the worker's sense of pressure combined with a consistent rhythm is a skill that often takes years for newcomers to master. After several hours of continuous processing, the result is bundles of raw fibers free of sap and retaining their full length, but still high in moisture and prone to discoloration if not washed and treated promptly. The raw fibers are then washed repeatedly with clean water, sometimes combined with mild biological enzymes to remove sap and impurities without damaging the fiber structure. Some facilities may use warm water to improve cleaning efficiency, or for fibers intended for paper production and coarse materials, apply stronger heat treatment to shorten processing time and reduce costs. Finally, the fibers are dried under natural sunlight or at low temperatures until they reach standard moisture levels, a process that typically takes at least 2 days. In major banana growing countries, such as the Philippines, India, and Indonesia, banana fibers are traditionally sun-dried on bamboo racks or raised wooden frames under natural sunlight, allowing the fibers to dry evenly while maintaining their light color and strength. Once dried, the banana fibers become lightweight, durable, and flexible, ready to move on to sorting, spinning, and industrial production stages. Tens of thousands of tons of banana fiber are collected and sent to industrial textile mills and fiber processing facilities, where it is determined whether they will become fabric, rope, or natural mats. Once inside the factory, raw banana fiber must undergo the most fundamental and critical step, carding. Here, fiber bundles are loosened, straightened, and aligned in parallel, while short fibers, broken strands, and remaining impurities are removed. This process standardizes fiber length, fineness, and uniformity, creating a solid technical foundation for the subsequent spinning and weaving stages. After carding, the fibers are fed into the spinning system, where they are twisted under tightly controlled tension and speed. In actual production, banana fiber is rarely used in its 100% form, but is commonly blended with cotton, linen, or other bio-based fibers to enhance softness, strength, and weavability, meeting the demands of industrial manufacturing. The result is stable yarn wound into spools, ready for weaving, carpet making, or the production of finished textile products. Depending on the intended use, the yarn is fed into shuttle looms, knitting machines, or braiding machines to produce fabrics, bags, mats, or technical materials. Compared to cotton, this material stands out for its higher tensile strength, but requires blending to improve softness. When compared with jute, banana fiber is lighter and more flexible, allowing it to be used in products with higher aesthetic requirements. In packaging and interior applications, its load-bearing capacity and stability in humid environments give it an advantage over many other plant-based fibers. In sustainable fashion, it is seen as an intermediate option, balancing performance and environmental impact. In terms of cost, a garment made from banana fiber or banana-blended yarn currently sells for about 20 to 40% more than a standard cotton garment due to higher collection and processing costs and the still limited scale of production. This remains the main barrier preventing banana fiber from becoming mainstream, as supply chains are still in the process of expansion and optimization. Each year, hundreds of millions of tons of banana trunks are reused instead of being burned, helping to reduce emissions by 20 to 30% in countries where bananas are a major crop, easing environmental pressure and turning agricultural byproducts into part of the solution for a global green economy. According to the United Nations, more than 400 million tons of plastic are discarded worldwide each year, much of it persisting in the environment for hundreds of years, forcing humanity to seek solutions based on natural materials as practical and necessary alternatives. Among zero-waste materials, bamboo has emerged as a leading choice thanks to its rapid renewability, high durability, and low environmental impact. And one of the most talked about household items today is the bamboo toothbrush. To produce toothbrush handles that meet quality standards, bamboo selected must be 3 to 5 years old, when the fiber structure has fully developed and reached its highest stability. After harvesting, the bamboo is transported to the factory and cut into moderately long sections suitable for preliminary processing. These sections are then split lengthwise into uniform billets with consistent cross-sections. The entire cutting and splitting process is automated using industrial saws, splitting machines, and conveyor systems, ensuring high precision, stable output, and reduced material waste. Next, the bamboo is soaked in a mild biological solution to remove natural starch and sugars, preventing mold and insect infestation. This step is critical to the product's durability and safety in use. After drying and reaching the required moisture level, the bamboo is shaped into handles. Each bamboo blank is fed into the machine and cut, contoured, and rounded according to preset molds, forming ergonomic handle shapes that fit comfortably in the user's hand and meet everyday use standards. Advances in CNC machines and automated sanding technology make this process more precise, consistent, and efficient, while also reducing material waste. The head of the handle is drilled with small holes in a standardized layout, preparing it for the bristle insertion stage. This step is carried out using high-speed CNC drilling machines capable of producing hundreds of holes per minute with near-perfect precision. Thanks to advanced automated control systems and sensors, the position and depth of each hole are fully synchronized, ensuring consistent quality at industrial scale. The next step is bristle insertion. Despite being an environmentally friendly product, the bristles of bamboo toothbrushes are still primarily made from nylon, a limitation that has yet to be fully replaced. This is because nylon currently offers the best combination of durability, elasticity, and safety for gums according to dental standards. However, compared to conventional plastic toothbrushes, bamboo handles are biodegradable, significantly reducing the amount of plastic waste remaining after use. After bristle insertion, an automated trimming and polishing system evens out the bristle length and rounds the tips, ensuring a smooth surface and safe contact with the gums in accordance with dental standards. Once completed, the toothbrush is printed with brand logos using automated inkjet printing or laser engraving, ensuring clear, consistent, and long-lasting markings on the bamboo surface. Finally, the toothbrushes are sterilized and inspected for bristle retention and surface finish before being packaged in paper-based or recycled materials, minimizing the use of plastic.